Welcome to the pre-class video assignment for section 1.2. Um, so in this video, we're going to cover the first 2 pages of the class notes. The remainder of those notes is what we will be covering in class. So as you watch this video, you will see pop-up questions through My Open Math, and those are what you will want to complete for a grade. So you want to work on those as we go through this video. So let's get started. Again, 1.2 is about some of the basic concepts and the basic terminology for DEs. We did see this, you should have seen this a little bit in section 1.1. A differential equation is an equation that relates some unknown function, or possibly functions, but for our purposes, an unknown function to their derivatives and possibly higher derivatives. So basically the comparison here is an algebraic equation, like we're used to seeing in algebra, is an equation where the unknowns are numbers, and to solve an algebraic equation is to determine which number or set of numbers make the equation true. In a differential equation, we have an equation where the unknown thing is a function, and in solving a differential equation, the goal is to find what is the function or what is the set of functions that make the differential equation true. So we saw a little bit about that in 1.1. Some notation and what have you here. Generically, we can describe a DE as follows. Here, the f of x comma y prime, this guy right here is really just meant to say that on the left of this equation we have some sort of expression involving possibly x, y prime, y double prime, all the way up to some order of derivative y to the n, and equals 0. So any DE could be thought of in this manner. So that is basically what is described here. So quick couple of examples. That is, here is an example where on the left we have this expression. It involves x, y, there's y prime, there's a y double prime. So this is this generic function on the left, and this is a differential equation because the unknown function is called y, and we have an equation involving y and it's some of its derivatives. So the first one here, this one was in prime notation. We can equally well describe a DE in Leibniz notation. So that's this dy dx type notation. So we will be using both throughout the course. So we want to be familiar with both of these. In fact, Leibniz notation has certain advantages, as we will talk about. So the first concept here about DEs we want to consider is something called the order of a DE. The order of a DE is the order of the highest derivative that is present in the DE. So, for example, the two DEs up here, this one here has a y double prime in it. That makes this one a second order DE. It has a second derivative in it. Over here, this one's a bit more of a trick question. Y to the 4 here, this would be read as an exponent, not a derivative. So that doesn't count, but this would be a derivative. That is a third derivative of y, d3y, dy3. So that one there would be a third order derivative. So this is a fairly easy concept, although again, there can be a couple of slight tricks here. So work through these following examples. The first one here, number A, this one clearly only has a first derivative in it for y, so this is a first order DE. This second one has a second order derivative, a second derivative here. This would be a second ordered differential equation. Notice that just because it has a second order derivative, it has no first order derivative. That's fine. A second order DE has to have a second order derivative and may have a y prime and may have a y in it, but does not have to. And the last one is the trick question. We would read this as follows: dx dt to the power of 3, that is a derivative raised to the third power. That's a first derivative raised to the third power, not a third derivative. This is a second derivative. So this part C here would be a second order dE. So again, this is somewhat subtle with the notation, but again, not generally. Once you've seen it, it shouldn't be terribly difficult. Another concept here is generally we like DEs often in something called normal form. The normal form of a DE is when you take your DE and you solve it for its higher order derivative. So in a first order derivative, the highest order derivative is a first derivative, and writing that DE as first order as first derivative equals, and then on the other side, notice this is just some sort of expression involving x's and y's, no y primes, right? Because we have solved for the y prime on the left. Again, normal form for a second order would have the second order derivative on the left, and therefore on the right, we would have some sort of expression involving x, possibly y, and possibly a first derivative dy dx, and so on. So as an example, briefly, fairly easily here, if we take this first example we had up here, and we put it in its normal form, it would look like this. And again, this is nothing more than solving for y double prime. Okay, so other things we want to think about here, some other terminology. There are a couple of broad classifications of DEs. We have ordinary differential equations and partial differential equations. An ordinary differential equation is an equation involving normal Calc 1 type derivatives. dy dx, y double prime, and so on are all ODEs. If you have had some Calc 3, you will have seen things called partial derivatives. So partial derivatives are things that look like, we'd write them this way and read them as saying this would be read as del W del X, del W del Y. So the del is basically telling you that this is a partial derivative. Again, that should sound familiar if you've had Calc 3. If you have not had Calc 3, don't overly worry about it at this stage. The good news here is we are not studying PDEs in this course, so we will not be talking about how to solve these things, but we will need some of this concept from Calc 3. The idea of a partial derivative is something we will run into in this course. Again, it is actually, even if you've not had Calc 3, it is not terribly difficult, and we will talk about it and learn about it when we get there. So we are only studying ODEs in this course, not PDEs. All right, one more little distinction here. Again, I mentioned earlier the idea of using Leibniz notation versus prime notation for derivatives. So we're familiar with Leibniz, usually in Calc 1. Calc 1 students don't like Leibniz notation because it's kind of ugly and hard to write. Prime notation is, of course, much simpler to write. But for DEs, as I will demonstrate here below, the Leibniz notation does have some advantages. So as a little example here, take a look at these two DEs here. This one here, xy prime plus 3t equals ky. This one basically says exactly the same thing. It says x times the first derivative of y plus 3t equals ky. So again, as a DE, the unknown in a DE like this is a function. So presumably here, since we have a y prime, the unknown function here is called y. And so the question is, well, if the unknown function is called y, what is its independent variable? Y equals f of what? What is a function of which variable? Again, in algebra, we're pretty accustomed to having y be a function of x, but we often have y equals a function of t. And if we were being weird, there's another letter here, K. How do we know this is not Y equals a function of K? And the point with prime notation is nothing about prime notation tells you which letter here is playing the role of independent variable. In Leibniz notation, however, we are being told it says dy dt. This is telling you that the name of the function is y and the independent variable is called t. So the function we are looking for here that fits this description would be y equals some sort of function of t. That also tells us then if y is the function, i.e. y is the dependent variable and t is the independent variable, then any other letters like the x and the k here would be treated as constants, basically. They would have to be parameters of something or just constants. They would just be numbers. So this is a useful little piece of information that we get from Leibniz notation that we don't get from prime notation, and sometimes that is a helpful advantage for Leibniz notation. So just a couple of examples here. All right, so for the following, what is the order of the DE? That should be pretty easy. And then determine the dependent and independent variables and any constants. So let's just talk about those real quick. So in this first example, this is fairly clearly a second derivative of x. This is a first derivative of x. So apparently this is second order because that's the second derivative is the highest derivative present. Notice in Leibniz notation, since this is dx dt, that tells us the dependent variable is x, the independent variable is t. So the function we are solving for here, would be solving for here, is a function called x of t, or x equals f of t. Therefore, any other letters not accounted for, that is the A and the K are simply constants in this example. All right, here's another one. This is actually something, a famous one for DEs. This is something called a logistic equation, but we can read this here. We've only got the one derivative here, dp dt. Therefore, this is first order. Clearly then the function is p. Well, that's, again, the dependent variable is p, and it depends on the variable t. So dependent variable is p, independent variable is t. Therefore, any other letters, the k and in fact the capital N here, these would have to be treated as constants. All right, so I'll let you look at the last one here. It is a very similar idea. But again, hopefully you get the sense that the Leibniz notation actually gives us a little bit more information than the prime notation does. So that's basically the first 2 pages of the this. The only other thing I wanted to look at here is some prerequisites for DEs and for this section. If you have had your calculus sequence recently, then this is probably pretty straightforward for you. But we need to talk about, again, some of the prerequisite skills you need will be you need to be able to take derivatives. So we haven't learned how to solve any DEs yet. However, we will see later in this section that if we have a DE and we have a function and we want to check whether the function is a solution to the DE, we can basically substitute it in to the DE by taking derivatives. And then we can plug it in and see if it is a function that solves the DE. Hence, we do need to be able to take derivatives to do this. So again, you want to be good with your derivative rules. If you haven't seen this in a little while, perhaps this is a chance to brush up a little bit. And again, probably the biggest, the main rules here for derivatives are the following. So the product rule tells you how to do the derivative of a function times another function. Derivative of f times g. Again, the big thing to guard against is the product rule is not what you would expect it to be. The derivative of f times g is not f prime times g prime. The real product rule should look familiar to you, and you have the opportunity here to try a couple of examples in my open math. All right, then. Naturally, then next we have the quotient rule. The quotient rule tells you how to do the derivative of f divided by g. And again, most importantly is to remember it is not f prime over g prime. It is a bit more complicated formula, something like this. So again, take a minute here and try a couple of these for practice. And then the last big derivative rule is something we call the chain rule. The chain rule tells you how to do the derivative for a composition of functions. That is, when g is inserted inside of f, what is the derivative? And again, there is a rule for this. The derivative of f composed with g is f prime with g inside it times g prime. So again, these are can be fairly easy, but sometimes the easy ones, ironically, are often missed. They're almost too easy. They're easy to trip up on. And that is just, for example, things like this. What is the derivative of e to the 3x? The derivative of e to the 3x is e to the 3x times the derivative of 3x. So 3e to the 3x. It is not just 3x. And again, it's an easy one, but it's also easily skipped over and not applying the chain rule to it. Again, so here's a couple of examples to try. All right, so that is it for our pre-class video assignment. You can go back and rework the problems. If you go to the assignment, you can have use the little drop-down menu to go back to these questions if you want to try them some more or make sure you get them all right. Otherwise, we will continue and finish the rest of this section in class. All right, thank you. See you in class.